Hello, in this video I'm going to take a look at the conical pendulum. Now, conical pendulum is interesting in its own right, but it also gives a nice link between circular motion, which is what we've been looking at in the last few videos, and then oscillations, which is our next topic. And those two topics are very closely related, and this is going to help us sort of bridge from one to the other. When you think of a pendulum, the chances are you're going to be thinking of string, mass on the end, and that mass is swinging backwards and forwards in a vertical plane. Conical pendulum isn't far off that, it's just a variation on it, whereas rather than going backwards and forwards in this vertical plane, it's moving in a circle, a horizontal circle. So that gives us, that's why it's a conical pendulum, because if you think then of what the string is doing, the string is sweeping out the sloping surface of a cone, and the mass is moving around the circle at the bottom of the cone. So that's why it's called a conical pendulum. And when we analyze this using our skills in circular motion, we're going to see that this can be used as a timekeeper in the same way as the regular pendulum is. So yeah, we'll see that when we get to the bottom of all of this. I'll draw out a picture of our situation. There's our string. I've exaggerated it a bit because we need to be able to see everything here. This angle theta is our angle with the vertical. We've got a mass on the end, which is going to have a weight of mg hanging down. We've got the tension in the string. We're going to say that the length of the string is length L. The radius of the circle is R, and the object is going to be moving with a speed v in this horizontal circle as it goes round to make the conical pendulum. So that's all good. We know that we've got various relationships between these things. So we know that the velocity is 2 pi r, because that's the circumference of this circle that the mass is moving through, divided by the period. So usually we use capital T for period. I've already used that for tension, so I'll go for a capital P on that one. So P is the period. We've also got a relationship between L, R and theta on all of this as well. So R is L sine theta, and we will see that that's going to be useful later on. But our analysis, as we've seen in all of our circular motion stuff so far, is we're doing Newton's second law, and we'll resolve vertically, we'll resolve horizontally. There's no motion vertically, so we've got that T cos theta is equal to mg, and we've got our centripetal force going on in the horizontal direction, that's T sine theta, and that is going to be equal to mv squared over r. This gives us an opportunity when we're solving these of eliminating t and m because they're in both equations. So we can rewrite the top one as t divided by m is g over cos theta. So that's going to be useful. So we've got, I can't remember what I said now, t divided by m is g divided by cos theta. Yeah, so g divided by cos theta. So that's got to be t over m on the other side, the second equation. So that's v squared over r sine theta. So they've got to be equal. We know what the, well, we've got v. It'd be nice to get rid of r because r is a lot more difficult to measure than L is. L you can measure just by, well, measuring the length of the string before you start. Once you've started moving this thing around in a pendulum, getting what r is a lot more difficult to work out what it is. So let's get rid of our r's, which is all on the right hand side of our equation here, because we've got 2 pi r over p all squared. So I'll change that to squaring it as I go. So 4 pi squared, and we've got r squared, so that's L squared sine squared theta divided by p squared, and then we can replace this r at the bottom, which gives us an L sine squared theta. So we can cancel quite a lot of stuff out of all of this. So the sine squared thetas disappear, and the L at the bottom and one of the ones on the top disappears. So this is looking pretty good. Now, the interesting thing out of all of these is going to be the period, because, you know, pendulum, you're thinking of it as a timekeeper, and that's going to be the interesting finding in all of this. So we can say that P is going to be equal to, well, let's say with P squared, let's not get carried away. So 4 pi squared cos theta, oh, I've got an L as well. So I'll just sneak that L into there, and then divided by G. So P is going to be equal to 2 pi, the square root of L cos theta divided by G. Right, so that's good. Now, theta, so we're saying here that for a particular angle, whatever the angle is, we've got, you know, theta we can fix, L we can fix. Well, L is fixed, it's the length of the string, G is just a constant, pi is a constant. So if we can keep this pendulum moving with a constant angle with the vertical, which is easier said than done, because as it loses energy, that angle is going to decrease. But if it does have a constant angle, then we've got a constant period of oscillation. So we've got that as a timekeeper. So what happens then if this angle is decreasing? How much is it going to affect the period? Well, if you think what's going on with cos theta, for a small angle, cos theta is pretty much equal to 1. So if theta is small, then cos theta is roughly equal to 1. And it's something that, I mean, you see that from the graph when you draw it out. You know, it's pretty flat at the start, isn't it, cos theta, and then it starts dropping off. So we've got a bit of slack here before we start getting a big change in the value of cos theta. If that's our 1, we've got a bit of slack here in angle. And you can try this out on a calculator as well and look at it. Well, what's going to happen if we wanted to drop down to 0.99 rather than 1? Well, that is at, just looking at the calculator, that's 8.1 degrees if you do inverse cos of 0.99. So anything up to 8 degrees, we've barely got any change in the period, particularly as we're going to square root that. And the square root of 0.99 is pretty much 0.995. So up to 8 degrees angle with the vertical on a conical pendulum, we've got 0.5% difference in the period of oscillation, which is not a lot. 0.5%, yeah, that's not bad. Obviously, we've got better ways of keeping time nowadays, but back in the day, or even now, if you want to have you want to go old school and you want to have something mechanical for working out time, this isn't that bad at all if you're losing 0.5%. And that's if you go all the way up to 8 degrees. I mean, you know, if you've got something which has got a smaller angle on it, then yeah, that's not looking too bad. So yeah, this is how we can have a conical pendulum as a timekeeper. And we're saying for small angle, P is 2 pi root L over G. And this is something that we can then compare in oscillations to when we analyze a regular pendulum and see what the period of oscillation of that is. But it's another standard result we can use as well for a conical pendulum. If we're going to set one of these things up and set it in motion, and we might build 4 or 5 of these in the same room, so they've all got the same G because they're all the same acceleration due to gravity if they're close to each other. We can vary the period of the oscillation based on the length of the string that we're going to set up. Do you want a 1 second, 2 second? I mean, you can set it up for whatever you want based on the length of the string. So say we wanted a period of 1 second on this. Well, this is going to be quite straightforward to work out. If we do 1 over 4 pi squared multiplied by G, then that is going to give us a 1 second period. Just trying to find my calculator to type that one in. So yeah, what length string are we going to need for that? Say we were going to have 9.8 for G divided by 4, and then divided by pi squared. So if we've got it's 25 centimeter string by the look of it. So yeah, if we got a 25 centimeter conical pendulum, then we've got a 1 second ticking clock. So yeah, nice. Like I say, this is just moving us into something we can compare to oscillations when we get on to the next type of pendulum.